Okay, so we're going to explore what lies above Pascal's triangle in the sense of trying to extend the pattern going upwards rather than going further down. So the key pattern that defines Pascal's triangle is that every number, for example this 3 here, is the sum of the two numbers above it. So if we want to extend this upwards, let's first of all just look to the side of the Pascal's triangle. So with this 1 here, we need this to be the sum of the two numbers above it, so we just have 1 plus 0, and similarly this 1 needs to be 1 plus 0. So we actually get a lot of zeros here on the outside, and similarly for this 0 to be the sum of the two above it, you just need more zeros. And it's not actually particularly interesting on the side, and you get the same over on the left as well. You just need lots of zeros in order for the pattern to be preserved. But things get a bit more interesting when we try and go up a row now, and we'll find that instead of it just being lots of zeros, there's actually a bit of choice over which numbers we could put there. So if you think about the two numbers above this 1 here, let's call them A and B. We're going to have a bit of choice over which values of A and B we can choose, so long as, we'll just write it down here, we need A plus B equal to 1. But we can find that whichever values of A and B we choose, we can generalise this over onto the right, so we've got B here, and then its sum with negative B would make 0, then to get another 0 here we need positive B, and the next term here is 0, so we need another negative B, and so on. So we get this positive negative pattern with our B's, and similarly going off to the left, this A would need to be followed by negative A, then followed by a positive A, and so on, so that we get zeros underneath. So we need to think carefully now which values of A and B can we actually choose so that it's a sensible generalisation of this pattern. And we can think of this as, if we want to generalise not just the property that each number is the sum of the two values above it, but if we also want to extend this really important property in Pascal's triangle that each row corresponds to the coefficients in a binomial expansion, then we'll find that this is quite helpful in determining some sensible values of A and B. So just to explain this, we've got in this bottom row, for example, if you look at the binomial expansion of 1 plus x to the power of 4, these are the coefficients of your different powers of x. You've got 1 plus 4x plus 6x squared plus 4x cubed plus 1 times x to the 4. And similarly, if we go up a row, we've got the coefficients in 1 plus x cubed, then 1 plus x squared, and the row above is just 1 plus x to the power of 1, and we can think of this top row as being 1 plus x to the power of 0, where we've just got 1 is our constant term there. And now if we go up into the row above, it makes sense for this to correspond to coefficients of x in the expansion of 1 plus x to the power of negative 1. So now we can actually use the binomial series expansion to get some sort of expression with coefficients of x. So I'll state this result a bit more formally later on, and I'll include something in the description to explore this in more detail, see where it comes from. But we can state this here for the power of negative 1. 1 plus x to the negative 1 is just going to give us 1 minus x plus x squared minus x cubed, and we keep going alternating between positive and negative powers. And this turns out to be equivalent to 1 plus x to the negative 1, at least for small values of x. So this is when x is between 1 and negative 1, or when its modulus is strictly less than 1. And we will return later on as well to actually what happens with bigger values of x, but we'll return to that at the very end of the video. So if we want this to be our series expansion of 1 plus x to the negative 1, and if we want to follow this pattern of, it seems along this diagonal here, these 1s are all of our constant terms, so it makes sense that this b here should actually be our constant term following this pattern along. And here we've just got 1, so we take b equals 1, and this actually matches up with what we predicted of having positive, negative, because here the coefficients are just negative 1, and here it's positive 1, negative 1, and so on. And it turns out that with this, a is actually just going to be 0, so over on the left we've just got 0, 0, and 0. So now I'll fill this in our top row, and then we'll have a look at extending this to the row above. And now if we want the next row to correspond to the coefficients in the expansion of 1 plus x to the negative 2, here we'll just state what this expansion is. Again, for the modulus of x being less than 1, we get 1 minus 2x plus 3x squared minus 4x cubed, and so on. So we get this nice pattern of 1, negative 2, 3, negative 4, 5, negative 6. And where do we actually put these above Pascal's triangle? Well, we can continue this pattern here of this diagonal line of 1s being our constant term. So we need to put our constant term 1 here, then our coefficient of x, the -2 would go here. You can see 1 plus -2 does give us the -1, and similarly when we put our +3 in, the sum of these two gives us the 1. When we put a -4 in here, the sum of these two gives us our -1, and this would continue along. We could actually put in some more 1s and -1s, and you can see we've got 5, -6, 7, -8. And this does seem to work, although we haven't really proven anything yet. We're just checking that this pattern does actually work when we put the values in. So now if we want to go up a row, let's first of all deal with the stuff on the left-hand side here. We've got, actually to make 1 here, it's just 0. So again, it's just more zeros going off to the left. Whereas working above, we can add in some more interesting terms here. So for 1 plus x to the -3, we'll put our constant term 1 here, then our next term would be -3, which we can put here, and the sum of these two does give us the -2 underneath. And this seems to work again where we put in our 6, our -10. And then we can actually use Pascal's triangle here to work out what the next terms are going to be here. So we can work this out as which two numbers you need to add together to make 5, or it's quicker to think of this as 5 take away this -10 gives us +15. Here, -6 take away 15 gives us -21, 7 take away -21 gives us +28, and -8 take away 28 gives us -36. So we're actually getting our triangular numbers just alternating between positive and negative for this row above. And again, we've just got lots of zeros going off to the left. And then finally, let's add in this row above, this 1 plus x to the -4 coefficients. So we put in our 1, just our constant term, then we've got -4 from the binomial series expansion here. And again, this seems to work. Then the next one we would have 10. Again, this works. -4 plus 10 gives us the 6. And similarly, we can put in now, we'd have -20. And again, this seems to work. And you could actually use this, if this is going to work, to find even more terms here. So you could do 15 minus 20 gives us 35 and keep going along here. But if we go upwards, you might actually see, when we put our 1 in there, you might see a pattern emerging. So if we just focus on all of the terms here, so if you spotted, this is actually a rotated version now of the original Pascal's triangle. We've got 1 followed by 1 and 1, 1, 2 and 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, and then you'll find that the next values which actually work here will be -5 and 1. So we seem to just have another copy of Pascal's triangle that's been rotated round. We've also got along each of these diagonal lines some negative values here. I think this is really interesting because this actually gives you a nice way of, you could, starting from Pascal's triangle, either extend upwards or add in some negatives and use this to find the coefficients in the binomial expansion for certain negative integer powers here of 1 plus x. But we haven't really proven anything yet, and what we'll do next is focus on actually proving that this result does hold and that this will generalise further upwards for all of these negative integer powers. Now if we want to turn this into a more rigorous proof, we're going to use as our starting point this result about the binomial series expansion. So we won't prove this result here, but again I'll include something in the description so you can see where this result is coming from. So now this result is telling us that when the modulus of x is less than 1, and this actually works for any real power, so it doesn't even necessarily have to be a positive or a negative integer n, this tells us about the series expansion to what our coefficients of different powers of x are. So the coefficient of x to the k is given by this fraction where in the numerator we've got this product n times m minus 1 times m minus 2 all the way down to n minus k minus 1. And our denominator we just divide through by k factorial. And the reason this works for positive integer powers of n, this might look a bit strange, but eventually in this product after a certain point you'll just get a 0 in there, so all of the terms after a certain point are 0 when we've got a positive integer power of n there. So now let's look to how we can actually use this result to prove that Pascal's triangle can be extended as we've seen upwards with the binomial expansion for negative integer powers. So what exactly do we want to prove? Well, all we really want to prove is that any two numbers above another one in between, their sum is going to give that number, or the coefficient, that lies underneath it. So we think really carefully about what all of these numbers represent. So here you might have your kth term, and then you've got your k plus 1th coefficient. And the one underneath is also going to be, just following this pattern because they've shifted along to the left slightly underneath, this is also going to be the k plus 1 coefficient, but for a different power. And if we're working downwards here, we've got, these were the coefficients for n is -2, then we had -1, then this row here was just a power of 0, where we've got 1 followed by lots of zeros. So we're actually going down from, if we call this row here n, then this row underneath is going to be row n plus 1. So we go from -2 and add 1 to get down to the row underneath. So what we essentially want to show then is, let's introduce some notation. We want to say that the kth coefficient in the expansion for n plus the k plus 1th coefficient, again in the series expansion where we've got n, is equal to the term underneath. So we want this to always be true, and this is the k plus 1th term, but now because we've gone down a row, this is for n plus 1. So now let's express this in terms of the result we've got for the binomial coefficients from this series expansion result. So here we've actually got, this term is the kth coefficient for a power of n. So what we want to show is that n times n minus 1, and so on down to n minus k minus 1, all divided by k factorial. When we add this to the next term, so we replace k by k plus 1, so we go down from n minus 1, all the way down to, we'll have n minus k minus 1, but then we've also got n minus, it will just be k plus 1, take away 1, so just n minus k is our last term. And because we replaced k by k plus 1 here, we've got k plus 1 factorial. So we want to show that this sum is equal to the corresponding term where we've got k plus 1 and n plus 1. So again, using this formula, our product, because we're up to n plus 1 now, starts at n plus 1, then times n, and so on, all the way down to n plus 1 minus, instead of it being k minus 1, we've replaced k by k plus 1, so this becomes just k in the brackets there, and then we're dividing through by, again, k plus 1 factorial. So if we can show by adding these two fractions that we get this fraction here, then this is effectively proving for us then that this pattern continues. And because this series expansion result is valid for positive and negative values of n, this would actually show then that Pascal's triangle can be extended both upwards and downwards, as so. So when we work with the sum of these two fractions, it's really helpful to notice they actually have a lot of factors in common. So if we write the left-hand side of this equation just as the left-hand side, we can actually take out a factor of this entire first fraction, because that's common to each of these fractions. So we've got n times n minus 1 all the way down to n minus k minus 1, all divided by k factorial. And then we've just got multiplying by 1 for the first fraction. Then the second fraction is the same thing, but we've added in n minus k in the numerator, and this k plus 1 factorial, we're just multiplying by another k plus 1. So we just have plus n minus k over k plus 1. So then this term in the brackets here, let's write the 1 as k plus 1 over k plus 1. We add this to n minus k over k plus 1. So you see here our k and negative k actually cancel with each other, just giving us 1 plus n, or we'll write it as n plus 1 over the common denominator of k plus 1. So all of this term in the brackets then is just n plus 1 over k plus 1. So our left-hand side can be written as n plus 1. We'll take it over onto the left-hand side, then multiply all of this n all the way down to n minus k minus 1. Then in the denominator we've got k factorial multiplied by k plus 1. So this gives us k plus 1 factorial. So now this looks a lot like the right-hand side. The only difference is we've got here n plus 1 minus k, but in our new expression we've got n minus k minus 1 in brackets. But it turns out here that if you do n minus k minus 1, take away the negative 1, this gives you a positive 1. So you've got, this is actually the same as n plus 1 minus k, just written in a slightly different format. So this is indeed equal to the right-hand side, which verifies our proof then and shows that we can indeed generalise Pascal's triangle by extending upwards, as we've seen, to include negative integers. I think what's really interesting here is because the binomial series expansion is actually valid for non-integer values of n as well, it turns out that you could draw a version of Pascal's triangle with non-integer powers, say for example to the power of a half or to the power of 1.5, 2.5, and work out the terms in these, the coefficients in this series expansion. Let's say if you start with a power of a half, you could work out 1.5, 2.5, or you could even extend upwards to negative a half, negative 1.5, and so on, just using the fact that we've shown this result holds in full generality here because n is allowed to be any real number. Now so far we've only looked at the series expansion valid where the modulus of x is less than 1, but we'll now see there's a neat trick that we can use to work with a series expansion valid when the modulus of x is greater than 1. So we think about the binomial we're expanding, 1 plus x. We can write this as this is equivalent to having x times 1 plus 1 over x. So here, even where the modulus of x is greater than 1, this is the same as saying that the modulus of 1 over x is less than 1. So we could work with the binomial expansion of this 1 plus 1 over x, because 1 over x is less than 1 in modulus. And we can just raise everything to any power n here, and this equation would still be valid. So this is our basis for now being able to generalise this result and see how this works when the modulus of x is strictly greater than 1. So if we start with, let's look at 1 plus x to the power of negative 1. If we rewrite this, we've got x to the negative 1 times 1 plus 1 over x to the negative 1. And now we can just use our previous result. We know the series expansion for 1 plus x to the negative 1, and we just replace our x by 1 over x. And this is valid because the modulus of 1 over x is still less than 1 here. So we can write this as x to the negative 1 times 1 minus 1 over x plus 1 over x squared minus 1 over x cubed, and so on, just using our binomial series expansion. And then if we multiply everything by this x to the negative 1, we get 1 over x minus 1 over x squared plus 1 over x cubed, and so on. So we seem to have a series expansion for 1 plus x to the negative 1, where the modulus of x is greater than 1. But now instead of having powers of x, like positive powers of x, we've got negative integer powers of x. But there's actually space for this in our picture with Pascal's triangle, because if you think about generalising this from having, here we've got our constant terms along this diagonal, then we've got our x to the power of 1, x squared, x cubed. If we go in the reverse direction, so x squared down to x, down to our constant term, it makes sense for this diagonal here to actually be coefficients of x to the negative 1. And of course, up till this point, all of the coefficients of negative powers of x have just been 0. But we could add in, we've got our coefficient of x to the negative 1 here is just going to be 1. So we could put a 1 here in our next row above Pascal's triangle. So this is equivalent to earlier we had the choice of a and b. So earlier we had 0 followed by 1. But now if we swap these, 1 and 0, you'd get lots of zeros off to the right as well. This corresponds to now, we're effectively getting the binomial series expansion, but valid where the modulus of x is greater than 1. And here you've got negative 1 as the coefficient of x to the negative 2, then positive 1 for x to the negative 3, and so on, going off to the left. And we can do the same sort of thing for, let's just quickly look at 1 plus x to the power of negative 2. So we write this as x to the negative 2 times 1 plus 1 over x, again to the power of negative 2. We can use what we know about the series expansion of 1 plus something to the power of negative 2, because we know that 1 over x has modulus less than 1. So our previous series expansion result is valid. We have 1 minus 2 times 1 over x plus 3 times 1 over x squared, and so on. And then multiplying throughout here by our x to the negative 2, we get 1 over x squared minus, we can write it as 2 over x cubed plus 3 over x to the 4, and so on. So this gives us a series expansion for 1 plus x to the negative 2, which again is actually going to match up with our row above here. So we start with the coefficient of x to the negative 2 is going to be 1, so that means we have a 1 over here now in this row, and this is just followed by zeros going off to the right, and then our 1 is followed by negative 2, positive 3, and so on. So you can actually see that we're going to get, and if we extend this further upwards, here you'd have 1, here you would have negative 3, and that would be followed by a 1 above. You can see we're actually going to get another copy of Pascal's triangle, but going up and over to the left above, followed by lots of zeros on the right-hand side. So this is really interesting that with our different choices of how we choose the two values above this 1 at the top of our original Pascal's triangle, you can get different types of series expansions valid for different values of x. And finally, we'll return to this initial position we were in, where we were interested in values of a and b, where so long as a plus b gave us 1, we could actually fill in this row above Pascal's triangle with b, negative b, b, negative b going off to the right, and similarly going off to the left with a and negative a. So we want to see if we can reconcile this situation with our understanding we've got now of this row above being the series expansion of 1 plus x to the power of negative 1. So we've seen earlier that this works with b as 1 and a as 0 as our first situation, and it also works with a as 1 and b as 0. That was where Pascal's triangle went off to the left, corresponding to the modulus of x being greater than 1 for our series expansion. And here we could think of this as being like a times 1 plus x to the negative 1 plus b times 1 plus x to the negative 1, where as long as a plus b is equal to 1, and these two have series expansions, then the sum of these two series expansions should give us 1 plus x to the negative 1. The only problem with this is, when we were doing our a terms going off to the left, this series expansion was valid where the modulus of x was greater than 1. So what we really had was a times x to the negative 1 times 1 plus 1 over x to the negative 1. We still had the same thing for b, b times 1 plus x to the negative 1. Now the series expansion for our a terms was valid when the modulus of x was greater than 1, whereas the series expansion for our b terms was valid when the modulus of x was less than 1. So you can see there's no values of x for which both of our series expansions would actually be valid, so the series wouldn't converge at all for any values of x, unfortunately. But I think it's really interesting though that we can think of this as having different values of a and b as being the sum of two different power series, even if they don't both simultaneously converge. And we could extend this going upwards as well, bearing in mind that this isn't actually going to be valid for any values of x, but we could do the exact same thing with negative 2, so you could have a times x to the negative 2 times 1 plus 1 over x to the negative 2 plus b times 1 plus x to the negative 2. And if you remember when we did our series expansion for the power of negative 2, there was no constant term when we had the modulus of x greater than 1, so going off to the left we didn't get a constant term. So this is telling us then that the constant term is just coming from our b terms on the right. So we can actually put in, following this diagonal for our constant term here, we've got b is just going to be our constant term, which then allows us to fill in the rest of this row. So you'll have, what do you add to b to make b? You've just got 0 there. What do you add to 0 to make a? You get an a. And then this will extend off to the right again. So you have here negative 2b, and then going off to the left you've got negative 2a. And then we can extend this going upwards as well. A, you've got positive 3a here. And then we would have, to make negative 2a, you'd have negative 3a here. You just have an a above. You'd have, going off to the right, above your b and negative 2b, you'd have first of all some zeros, you'd have a b here, you'd have negative 3b going off to the right, and we've got b's. So we get essentially two different copies of Pascal's triangle, just like we saw before, only where everything's been multiplied by a or multiplied by b going off to the right. And in between them we've just got lots of zeros like this. So this is telling us then that even though this series expansion isn't really valid for any values of x, we can still find something where, in terms of the values of a and b summing to give 1 underneath, and similarly for all the other terms, we could extend Pascal's triangle upwards like this for any values of a and b. And this choice of having b here as our constant term, we could even tweak this and get other ways of extending upwards as well if you're interested. So to answer the question, what lies above Pascal's triangle, first of all we had two different copies of Pascal's triangle, either going off to the right or off to the left, where we had some negative values involved. Or you could also, if you're not too fussed about your series being convergent for any values of x, you could also think about this as being two copies of scalar multiples of Pascal's triangle, again with the negatives involved there.